All right, 48. Write the Lewis structures for the following. All right, so with writing Lewis structures, we follow a set of steps. Right, first step is you have to know how the atoms are connected. Right, that has to be told to you, or you have to deduce it because it's simple. So, for example, with H2CO, you're told both hydrogen atoms are connected to the C along with the oxygen. All right, so with that said, we're given that. Next thing is you look at the atoms and you count up the valence electrons. These are almost going to be like a pile of electrons you're going to use to put this molecule together with. So oxygen has 6 valence electrons. Carbon has 4 valence electrons. The two hydrogens each have 1 valence electron, so that adds up to 2. So when you add them together, you got a pile of 12 electrons to play with. All right, so step 2 done. Step 3, bond everything together. So each bond is a shared pair of electrons. So 2, 4, 6 electrons to bond all of these atoms together. So the red lines represent 2 electrons apiece, a bonded pair. All right, so that's that step done. Now, with the remaining electrons, you want to complete as many octets, right? Get 8 electrons around as many atoms as possible. The rule is the more electronegative elements get the electrons first. And you don't share them out, right? I mean, you pick an atom and you try to complete its octet. So oxygen is more electronegative than carbon. So it gets these 6 electrons to complete its octet. So with the bonded pair and the 3 lone pair, you're going to have 2, 4, 6, 8 around the oxygen. And you're out of electrons. I mean, at this point, you're done. Now, the octet for carbon isn't complete. So the way we fix this is by borrowing one of these lone pairs and using it to make a double bond. So I make a double bond between the carbon and the oxygen, and now I have 2, 4, 6, 8 electrons around the carbon, right? All 4 of them bonded pairs, and 2, 4, 6, 8 electrons around the oxygen. 2 of them bonded and 2 lone pair. Hydrogen, of course, only bonds to shares electrons with one thing, and it's completed its outer level, the 1s. And that's it. So now we are done, right? So this is the molecular, the Lewis dot structure for formaldehyde. And we're finished. This is the Lewis dot structure for this compound. All right, so B. The constitution of hydrogen peroxide is everything connected in a row, right? The 2 hydrogens connected to each of the oxygens. Right, this is the constitution, how they're connected. Again, we count up the valence electrons from each of the atoms. So with the both oxygens, right, 6 apiece, we have 12 electrons being contributed to our pile from the oxygens. 2 hydrogens, 1 valence electron apiece. Add those together, you have 14 electrons to play with in putting this molecule together. Next step, we make bonds. Every bond counts for 2, so 2, 4, 6 electrons used to bond everything together. This gives us 8 electrons yet to be assigned. Complete as many octets as possible, so we put them around the oxygens. And this molecule is done. And this is the Lewis dot structure for hydrogen peroxide. All right, C, C2H6. All right, so the constitution for this is we have 2 centers around each of the carbons, and the fluorines are connected to the essential carbon. So we have a carbon-carbon single bond here. All right, so we count up the valence electrons. We have 6 fluorines, each of them having 7 valence electrons. So that adds up to 42. And we have the 2 carbons, 4 valence electrons apiece, so that adds up to 8. When we add them together, we have 50 electrons to play with. Next step, we connect everything together. So 2, 4, 6, 8, 10, 12, 14 electrons to bond everything together. This leaves us 36 electrons yet to be assigned. We take these 36 electrons and try to complete the octets for the fluorines. So with 36 electrons, I'm able to get 3 lone pair and 1 bonded pair around each of the fluorines. And I've completed the octet for the fluorines, and that's it. This is the formula for C2H6. Looking at D, As3, 3 minus. All right, so this is the constitution. Everything's connected to the central arsenic. 18 electrons for the oxygens, 5 electrons for the central arsenic. Now, this is the polyatomic ion, right? So, arsenide or arsenate. So it's got a -3 charge. So when we have a charge on our polyatomic ion, and it's a negative, we add electrons for each of the charges. So it has a -3 charge. So 3 extra electrons are injected into this Lewis dot structure. So I have 26 electrons to play with. Bond everything together. That's going to subtract 6 from my pile. 20 yet to be assigned. So I complete the octets for the oxygens, and the leftover goes to the arsenic. And this would be the Lewis dot structure for ASO3 3 minus. E, if we're doing sulfurous acid. Formal charge, right. So formal charge is defined as the valence number minus the electron count. So for this particular compound, we have formal charge. Each of the oxygens has a valence of 6, and the electron count is unbonded electrons, right, counted individually, 1, 2, 3, 4, 5, 6. And when you get to a bonded pair, you take 1/2 the bonded pair, 7. So there's an electron count of 7 around each of these oxygens, a valence of 6. So this gives me a -1 formal charge around each of these oxygens. And that's important because this Lewis dot, this compound has a overall -3 charge. So there has to be formal charge in this structure, and the formal charge has to equal the charge on the species. So whenever you have a polyatomic ion, there has to be formal charge in your Lewis dot structure. So that has to be included. It's part of the structure. All right. So there's a -1 formal charge in each of these oxygens. 1, 2, 3 adds up to -3. All right, E. We have H2SO3, sulfurous acid. This is the constitution. All right, the H's are connected to the peripheral oxygens. And we count up the electrons we have to play with. Right, so 18 electrons for the 3 oxygens, 6 electrons for the sulfur, 2 electrons for the 2 hydrogens. Right, so that adds up to 26 electrons to play with. All right, we bond everything together. That's the second step. 2, 4, 6, 8, 10 electrons to bond everything together. So I now have 16 electrons yet to be assigned. The oxygens get them first because they're more electronegative. And if there's anything left over, it goes to the sulfur. All right, so 2, 4, 6, 8, 10, 12, 14, 16 electrons. All right, so this is it. This is the Lewis dot structure for sulfurous acid. Now, like in the last one, there's formal charge here. All right, so we can see that oxygen on the end there that doesn't have the hydrogen has an electron count of 7. And 1/2 the bonded pairs around the sulfurs, 1, 2, 3, 4, 5 with the lone pairs. So formal charge is equal to the valence. Right? The valence for oxygen is 6. Its electron count is 7, so there's a -1 formal charge on that oxygen. The electron count for the sulfur is 5. Its valence is 6, so there's a +1 formal charge on the sulfur. When it's a neutral molecule, the sum of the formal charges has to equal the charge on the molecule. So if you have a -1 somewhere in there, you have to have a +1 to cancel it if it's a neutral molecule. So this would be the complete Lewis dot structure for sulfurous acid. All right, looking at C2H2, right, this is acetylene. We've got 8 electrons because of the carbons, 2 electrons for the hydrogens. That's 10 electrons to play with. There's a C-C single bond. So we bond everything together, 2, 4, 6 electrons for the bonded pairs. I have 4 electrons yet to be assigned, and they go around one of the carbons, right? Try to complete the octet of one of the carbons, right? Don't split them up. So I've completed the octet for this carbon, but I have an incomplete octet for the other carbon. So the way we fix this is we loan one of the lone pairs to make a double bond. All right, so now I have 2, 4, 6, 8 electrons around carbon 1, 6 electrons around carbon 2, so I donate another pair to make a triple bond. All right, so there's a triple a CC triple bond in acetylene. And this would be the Lewis dot structure. No formal charge, and that's it. All right, write the Lewis dot structure for phosphorus trifluoride. Okay, is the octet rule satisfied for all the atoms in the structure? I guess we'll see. So we count up the electrons, 18 electrons for the fluorines, 5 electrons for the phosphorus. That's 26 electrons to play with. 6 electrons for bonding everything together. That gives me 20 electrons yet to be assigned. 18 electrons around the peripheral fluorines, and that gives me 2 electrons left over to go around the phosphorus. So no, we haven't broken the octet rule here. Everything's got a complete octet. B, determine the oxidation numbers for the phosphorus and the fluorine. Well, first thing, before we do that, we have to make sure there's any formal charge. So the electron counts around the fluorines are 7. 7 minus 7 is 0. Phosphorus has an electron count of 5, a valence of 5, so there is no formal charge. So the way we treat oxidation state in these molecules is if we have a bonded pair, we act like the more electronegative element is taking charge. So those electrons are taken by the fluorine. So since phosphorus is bonded to 3 fluorines, it's losing 1, 2, 3 electrons of those fluorines. So it's got a +3 oxidation state. And each of the fluorines has a -1 oxidation state. All right, so that would be the oxidation state for the compounds, right? Oxidation state of phosphorus is +3, the fluorides are -3. There is no formal charge. Both the oxidation state and the formal charges are only estimations of molecular atomic charge. All right, so again, we look at this as complete transfers, even though it's a sharing situation where the electrons go to the more electronegative element. So we're trying to get where the charge is in this compound.